I guess the really important question here is, what is insulin resistance? And can you explain this to me like I'm a 10-year-old?
Oh yeah, for sure. Insulin resistance it's a disorder that has two parts. It's like a coin with two sides, that as much as we think of one side just because we hear the word insulin resistance, but there's another part to it that is very important. So insulin, first of all, is a hormone that we make from the pancreas, a long kind of gland tucked underneath the stomach. And the pancreas is a very busy organ. It makes a lot of different hormones. It makes hormones that come into the blood. It also makes enzymes that go into the intestines to help digest food. But among the hormones that are being released into the blood is insulin. Now, in the person with type 1 diabetes, their immune system has destroyed their beta cells. So they don't make insulin anymore. That's why for a person with type 1 diabetes, insulin is a life-saving therapy. You're giving them what they're not making anymore. But for everybody else, we have beta cells and they're releasing insulin when they need to. Now, usually the main reason the beta cell is releasing the insulin is because blood glucose levels go up.
So I eat sugar.
You eat sugar, or not even something as obvious as sugar, but bread or crackers,
White rice.
chips. Oh, yes. So basically anything that falls into the family of a carbohydrate. So if the earth grows it, that's a carbohydrate. If it's a plant, it's a carbohydrate. Maybe that's a better way of describing it. And so it's going to have starches and sugars, which all is kind of falls into this family of carbohydrate. Depending on how much starch or sugars that it has, then that will result in a bigger or smaller blood glucose or blood sugar response. But then if blood sugar is too high for too long, that becomes very harmful to the body. So insulin comes in and helps lower the blood glucose. And then having done its job, insulin comes back down.
So insulin comes out like a taxi and transports all the glucose in my blood to various places around the body to store them?
Perfect.
So
yeah,
it's
and
like
the
a
main...
taxi.
Yeah, that's right. You can look at it's a shuttle, it's a taxi saying, hey, glucose, come on in. I'm dropping you off at the muscle. So mostly, just as an interesting tangent of insulin, before I finish answering insulin resistance, insulin will open the doors for blood sugar to come in and drive the taxi in, mostly at the muscle and the fat. Muscle and fat tissue need insulin to come and bring the sugar in via taxi. However, other tissues, and the brain a little bit as well, other tissues will still respond to insulin, but they don't need insulin to tell it what to do with the sugar. It just takes it in. But even on those, like the liver, for example, if the liver sees sugar driving by in the taxi, it just opens the doors and lets it in. It doesn't need insulin to come and tell it to let the sugar in. However, even at the liver, and every other cell has a similar degree of this, the liver doesn't know what to do with it. So this is back to something I'd mentioned earlier, where insulin's thematic effect at the entire body is to tell the body what to do with energy in all of its forms as these kind of caloric-rich molecules, what to do with lactate, what to do with ketones, what to do with fats or glucose, what to do with amino acids. So insulin will tell the body what to do with all of those things. But again, its most famous effect is to control blood sugar. And that's not wrong, because its most powerful activator is blood sugar. So with all of that in mind, insulin resistance is two problems wrapped into one. The one problem is the most obvious one, which is that insulin isn't working as well as it used to. So back to the analogy of the taxis dropping off sugar, if the muscle tissue has become insulin resistant, insulin is coming and trying to pull the sugar-loaded taxi into the muscle, but the muscle's not listening.
So say that again. So the
insulin's
coming past with the glucose inside it.
Well, not technically. Yeah, but just to sort of go with your metaphor, but maybe to use another one, insulin comes and knocks on the doors. It's like the bouncer at the door. It's coming and knocking on the door of the muscle saying, hey, muscle, I've got some sugar that wants to come in. Mm-hmm. And normally the muscle will say, oh yeah, sure, okay, open it up the doors and let the sugar come in. When the muscle is insulin resistant, the bouncer's knocking. Maybe there's even, I'm almost getting ahead of myself, but one bouncer, maybe two or three bouncers pounding on the doors of the muscle cell, but the muscle cell's not listening. It's become deaf. That's the insulin resistance of what we call insulin resistance, where some of insulin's effects, like helping lower blood sugar, it's not working very well anymore. And the muscle is just an obvious example because there's so much of it. It is the biggest tissue on the average individual. Someone who's very obese perhaps now has more fat tissue, but even people who are overweight, most of us is muscle. So it's a good tissue to look at. So part of insulin resistance is that of all the things insulin's trying to do, including lower blood sugar, it doesn't do it quite as well as it used to. Some of the cells or tissues of the body have become deaf to insulin's demands. Now, however, at the same time that's happening, insulin levels are higher. And that is really important. And I'll mention an example in just a moment that highlights the difference between the two. But we have to consider anytime we talk about insulin resistance, we think of two things happening in concert. One, insulin isn't working quite as well as it used to in various places of the body. At the same time, insulin levels are higher. And that kind of takes us back to the muscle cell where I'd mentioned, getting a little ahead of myself, that a bouncer is knocking on the door. And once upon a time, the muscle cell would hear that one polite knock from that one bouncer, or one molecule of insulin, if you will, and it would open the door and let the glucose or the blood sugar come in. But now the muscle cell, the bouncer, insulin's knocking on the door, but the muscle doesn't listen. It's resistant. And so the body has adapted and it learns, okay, well, if one bouncer wasn't enough, let's send an angry mob of bouncers. And then the muscle will start to open the door. And indeed it can. So those two problems go together. On one hand, insulin isn't working as well as it used to. That's what gives it the name insulin resistance. But there's another part that is equally present, which is that blood insulin levels are higher. Now, earlier at the outset of the conversation, I mentioned that even infertility has an origin, has some degree of development because of insulin resistance. And it's a perfect example of both of these parts of insulin resistance, where in some instances, insulin isn't working very well. Always with insulin resistance, blood insulin levels are higher. So, for example, erectile dysfunction is the most common form of male infertility. In fact, its connection to insulin resistance is so strong that just a few years ago, I was so struck by a title of a paper that had just been published, which stated something like, is erectile dysfunction the earliest manifestation of insulin resistance in otherwise young, healthy men? Now, what is the connection? It's because in a normal erectile function, in order for the man to have normal erectile function, he has to experience a pretty dramatic increase in the size of the blood vessels in his body. The blood vessels expand, that increases blood flow, and then he has normal function. Part of that signal that tells the blood vessels that it's time to expand is actually insulin. And so this is what I said earlier, where insulin does so many things in the body, and we only think of it as being relevant to glucose, and that's not fair. Insulin does a lot of stuff, again, including telling blood vessels to expand. Now, unfortunately, in the case of this unfortunate man, his blood vessels become insulin resistant. So now it's insulin coming and knocking on the doors of the blood vessels saying, hey, it's time to expand and increase blood flow. But the blood vessels don't respond. They don't listen. So they stay constricted. Blood flow stays insufficient, and thus he has erectile dysfunction.
Look, I don't want to be insulin resistant.
No one does. No one does.
So tell me how it happens.
Yeah, right. Yeah. So the origins are so important because it helps us understand why we've gotten into the situation we are, where it's the most common problem worldwide. There are two pathways to insulin resistance. So two roads that get to the same destination. Again, the destination being insulin resistance. There's the fast lane, which I call fast insulin resistance, and it actually has 3 lanes, which I'll describe in a moment. Then there's the slow insulin resistance, which is it takes a little longer to get there, but at the same time, it takes a little longer to get away from it. So I'll start with fast insulin resistance because the slow one ends up getting a little excitingly complicated, but in a cool way. So with fast insulin resistance, there are 3 things that I could take you to a clinical lab and I could make you insulin resistant in 6 hours with either of these 3 things. But as quickly as it settles in, if I remove those things, your insulin resistance would go away. So these are fast causes, and they're fast resolution. They are stress, is a primary cause of fast insulin resistance. So too is inflammation. And then lastly, and this is going to sound somewhat paradoxical, too much insulin is also a cause. And I'll end with that one because I think it's the most important. Then transition to slow insulin resistance. So anytime the body is experiencing too much stress, it will very quickly become insulin resistant. Now, as a professor who teaches endocrinology, no surprise, I define stress in the context of hormones. And there are two primary stress hormones, cortisol and what we call in the US epinephrine, or in the UK adrenaline. Those are the two stress hormones. Now, those hormones are very distinct. They have almost nothing in common. But like when you are feeling a little stressed, it's both of those, especially adrenaline / epinephrine, that are making you feel a little jittery. It's making your heart beat a little faster. You're a little more alert. That all starts to play into a stress response. But what those two hormones have in common is that they both want blood glucose levels to climb. It's kind of their way of saying, hey, we don't really know what's going on right now, but we want to be ready to run away, that's the fight or flight kind of aspect to stress. And so they want to push blood glucose levels up, and they do very well. That, of course, puts them at odds with the hormone insulin, because these two, epinephrine or adrenaline and cortisol, the two stress hormones, they're pushing glucose up. Insulin wants to push it down. So the more the body has those stress hormones elevated because of, say, sleep deprivation, that's a very effective way to increase cortisol. Or they are drinking too much caffeine. That is a way to increase epinephrine quite strongly. If both of those signals are too incessant, or they continue to be present and climb, then insulin has to work harder and harder, and then we have insulin resistance. So stress is a cause of insulin resistance. But then next is inflammation. You and I were commenting about earlier about how, boy, there's a cold going around. It's flu season. Even then, if a person were wearing a continuous glucose monitor on the back of their arm, measuring their glucose levels, they would see their glucose levels are much, much higher, like significantly higher during the time that they're struggling with this infection. That is a reflection of insulin resistance. Insulin's having a harder time keeping the blood glucose levels in check. Anytime inflammation is up, insulin resistance will be up as well. Even in things like autoimmune diseases, there are reports in humans that document the degree to which someone has, say, active rheumatoid arthritis. Their joints are achy because of an autoimmune attacking of the joints. They will note on some days, like every autoimmune disease, there is an ebb and a flow. Some days it's good, some days it's bad. And on the bad days, if you measure their insulin resistance, it is absolutely locked with the degree to which their immune system is turned on or off, or higher or lower. So inflammation is another cause. And then the last one of the fast lane of insulin resistance is too much insulin itself. Now, the astute listener will realize the kind of circular thing I've just presented by invoking high insulin as a cause of insulin resistance, because they will also think, but wait a minute, Ben, you just said that high insulin is also a consequence of insulin resistance. That, back to the bouncer knocking on the door of the muscle cell, if one bouncer wasn't enough, or one molecule of insulin wasn't enough, the body will say, okay, well, let's send 10 molecules of insulin. So high insulin is both a consequence of insulin resistance, but it's also a cause. And this is reflective of a fundamental principle in all of biology, that if there is too much of a stimulus, a cell, if it's capable, will try to become resistant to that stimulus. This would be like a funny analogy of in the Bikman home. My darling wife is home with the children. That is what she wants to do. She is full-time mom. When I'm home, and I try to be home as much as I can, it's funny for me to note the difference in how quickly we each respond to our children. I will hear my child saying, "Mom, Mom, Mom," and she's not responding. Mom has heard this for so much that she's become kind of selectively deaf to when my children are demanding her attention. I'm not as around my children quite as much because I'm working during the day. And so when I hear that, it's a very fresh signal to me. I've not heard it so much that I've become deaf to it. And so I will respond even though I'm in the other room because I'm so much more sensitive to the clamoring for attention. This is like the body in response to insulin. If there is always insulin, it's always going up, the body will start to say, the muscle cell will start to say, boy, insulin, you are knocking on my door all the time. This is getting old. I'm not responding anymore. I'm not going to listen as much as I was before. So in that sense, insulin, too much insulin becomes a cause of insulin resistance. And back to what I said earlier, I could take you into the lab, start infusing you with just a little drip of insulin to increase your insulin, and over just a few hours, you would become demonstrably less sensitive to it than you were before we started. But again, as I take that away, give your body a few hours and it's back to normal. In every one of those instances, it's a fast onset and it's also a fast solution if we can take it away.
If we can take it away, but if we can't take it away, does it become sort of chronic?
Yeah, so at that, especially all of these can contribute to a more lingering insulin resistance, but especially insulin, where I focus on that one the most because of not only its relevance to the slow lane, but also just how present it is, where 70% of all calories globally are carbohydrates. And now, perhaps with the best of intentions, our experts are telling us that we should be eating 6 times a day. And so we wake up in the morning, insulin has finally been coming down while we've been fasting overnight. Insulin gets to take a little bit of a break. We're fasting. Then we break that fast by eating breakfast. And in the UK, as it is in the US, by and large, this is going to be a very starchy, sugary breakfast. It's toast with some jam, or it's cereal, or it's bagels. That is almost pure glucose. And so what do? We wake up, we eat breakfast, we spike our blood sugar levels, and insulin has to come up. Insulin will take longer to come down than the blood sugar will. It will wait in the blood to make sure that all the blood sugar has gone back to normal. So depending on how much carbohydrate we ate for breakfast, it could take our insulin levels 3 or even 4 hours to come back down to normal. Long before it's had a chance to come back down to normal, we've had a mid-morning snack, of course. We need to go get a sugary coffee and another bagel or something. And so after just a couple hours, we do it again. And once again, before insulin has had a chance to come back down, we have a starchy, carbohydrate-heavy lunch, then an afternoon snack, and then a carbohydrate-heavy dinner, and then, of course, we have to have an evening snack before we go to bed. So the average individual is spending every waking moment in a state of elevated insulin, and thus the signal never really goes away because they never give themselves a break. But one of the consequences of that I mentioned, which is that it directly causes insulin resistance. But when insulin is high, it starts to have a signal on the fat cell. And that then brings us to the slow insulin resistance, where you have something happening in the fat tissue that begins to set the stage for insulin resistance in the entire body. And it takes longer to settle in, but it takes also longer to go away. That's why I call this one slow insulin resistance. Now, in the case of insulin, most people, so the key with I'll explain it this way first. So the most relevant feature with fat tissue contributing to insulin resistance is the size of each fat cell. When we typically think of fat, we would maybe say, okay, Steve has, I'll do this in kilos for the UK audience. Steve has 10 kilos of fat on your entire body. That's probably too much for you. Ben has 20 kilos. And yet, it's possible that I'm healthier metabolically than you. And that's because it's not the mass of fat that matters most. It's the size of the fat cell that matters. This is why women, despite universally being fatter than her male counterparts, are healthier with regards to insulin resistance and every single metabolic problem. It's because women, as a result of her particular sex hormones, have more fat cells, but they're smaller. So she has more fat, but smaller fat cells. And small fat cells are healthy, insulin-sensitive, anti-inflammatory fat cells. But the bigger the fat cell gets, the more it initiates a cascade of events or a series of events that creates insulin resistance.
And am I right in thinking we have the same amount of fat cells for our whole life pretty much?
That's a really, really safe assumption for most people. Yeah, for most people, a fat cell, sometimes students will hear that fat cells are immortal. That is not true. But they're long-lived. Fat cells will live about 10 years. And so typically, By the time, if you look at a newborn, during infancy, childhood, and puberty, the number of fat cells is going up, 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 up. Once they finish puberty, so mid to late teens for a young woman, late teens or even early 20s for a young man, usually at that point, the number of fat cells they have is going to be very static.
If you love the Diary of a CEO brand and you watch this channel, please do me a huge favor. Become part of the 15% of the viewers on this channel that have hit the subscribe button. It helps us tremendously, and the bigger the channel gets, the bigger the guests.